Are there any questions? How many people have checked the truth of injectivity? You know what I'm talking? You know what I'm referring to? Daniel, what am I referring to if I say injectivity? Yeah, I'm sure you're speaking loudly and clearly enough for people within a certain radius to hear, but there's a fair amount of noise, and that we need to have that now. And okay, anyway, is that a yes or a no? I guess a qualified yes.
For the isomorphism from K0 to function.
Yeah. Okay, but then are you are you familiar with how that goes? Is that a yes?
No.
No. Okay, but have I indicated my take on that it's a corollary of surjectivity? Okay. Yeah. Okay, and the idea is that surjectivity applied to a different algebra, right? And what's the different algebra? Well, I'm going like this, right? It's have to be a little careful because there's paths. So this is paths of paths. In the first instance, the paths are closed paths. But if you have what we have is maybe yeah, you have to show if something in K0 is 0. No, you have to show if it's if it maps into 0, then it's 0. Okay, so in K0 is a difference of two things, right? Which are positive, which come from projections in matrix algebra. Okay, well, I mean, since it's a group, you only have to prove it's injective at 0 somehow. Okay, but this is convenient because it means that if you have the difference of two things, we want to prove that's equal to 0. That means we have two positive things, two projections, and we want to prove that that they are the same in K0, right? Which and for what? And what does that mean? Are you you're Justin. Okay, and so you know, if someone gives me half a minute, I can maybe remember the name. But so what are you, Jalal?
Yes.
Okay, good. Oh, that took me half a minute, I guess. Okay, and I like to fill it with talk in the meantime, so I can stall. Okay. All right, but then what if you have two projections or idempotents, let's say projections, which are equivalent in K0, Murray phenomenon? No, they're not for Murray phenomenon equivalent. But how do we get something which is Murray phenomenon? How do we reduce that to Murray phenomenon equivalence? Well,
I want to produce something that is Murray phenomenon equivalent. That's not.
Well, it's a general question. Suppose you have a semigroup, and you have two elements of the semigroup that are equal in the enveloping group. Then how can you restate that in terms of an equation in the semigroup? How many people remember that from just calculating with some universal enveloping groups? Vincent? When it's maybe hard to remember because in many cases, you look at the two elements of the semigroup. If they're equal in the group, they're equal in the semigroup. But that's not always true. Maybe it's not that easy to think of an example. Okay. Well, actually, I think it is. I mean, there are some semi-groups. It's easy to think of, here's an extreme example. There are some semi-groups such that, anyone want to think of an example? Where two elements of a semi-group are not equal, but they're equal in the enveloping group. Here's a hint. Remember what Professor Helmholtz says, always go for the simplest thing, at least until you can handle it. And yes, Lucy.
I think if we, or at least we've done this exercise before, if we take the semi-group to be the positive integers with infinity.
Yeah. Okay. Well then.
Is zero.
Yeah. So and so what then? So what's the answer to the first question? You have two integers, say 3 and 6, the positive integers, and the two things in the semi-group that are equal in the group. Then what do you have to? Then how can you patch things up so that how can you patch them up so they're equal in the semi-group? Anyone want to suggest? So we have 3 and 6 are equal, and the semi-group is the integer, the positive integers, the natural numbers, together with plus infinity. Okay, that's the and the addition is obvious. Yes, Carissa?
3 plus infinity is
Sorry?
like 3 plus infinity equals 6 plus infinity.
That's true, yeah. And maybe that's the best you can do, because certainly 3 is not equal to 6, right? And if you add any other single element to both, then you're still not going to be okay. But all right, okay, this is called failure of cancellation. So normally, if you're in a safe setting, reasonably safe setting, you can assume that cancellation holds, right? It says that the two elements of a semi-group are equal in a group, they're equal. But in general, you can add, it's enough to add something. You can add something and get to me. So, and in K0, that means we can add some other projection, right? The class that we had, the class with some other projection to both of them. And since that's, and once we do that, if we add any larger one, because the larger one would be this plus something else, right? Because add any larger one, then they would still be, well, then you're, well, yeah, the point is that you can, what you're adding, you can assume it's a multiple of the unit. And why is that important? Or maybe it's not important. But anyway, if you have two projections and they're equal in K0, you can add single projection to both. And since every projection is less than some multiple of the unit, you can add the difference. And so I think that's adding single additional thing to both. You can assume that you're just adding. But maybe we don't need that at the moment. We did need that when we were when we had the C minus F, so on. We were trying to prove half exactness. Okay, so we want to show that after we add some projection, maybe multiple of the unit, it'd be enough to add, well, I guess the point is it's enough to add some projection to get very fast. So we want to just prove that there are Markov equivalent if the corresponding closed loops in the suspension is a matrix node. Okay, so the idea is you look at paths of elements of the algorithm, not closed paths now, just paths of elements. So and what we would like to do is get the two projections, say E and F, least after we've added something to them, we'd like them to be we'd like them to be connected by a path, like connected by a path, because then they'll certainly be the same in because it'll be the same in K0. So the conclusion we want is they're the same in K0. It'll be I think that we can, we had proved we're going to get that they're the same, but we're going to get that they're homotopy, okay? But then they're actually connected by a path. But that well, that won't be true until we add something. There's got to be some point where in the proof we add something. But anyway, we have a point as you look at the algebra of paths in A, just paths parameterized by t going from 0 to 1, nothing to do with circling. And so this is this T-star algebra, you know, the soup form. And so you want to, well, we know surjectivity, so you apply surjectivity for the block periodicity map for this algebra. And and now we're assuming that and what does surjectivity say? It says that it's something, if you have a closed path of variables, then it comes from the homotopy comes in a standard way from some projection. Okay, but we're assuming that we have this sort of two paths in an F, or two projections in an F. We're assuming that corresponding closed paths are homotopy, some matrix of. And but then we know that that this means that that this we have that means there exists a single path of paths by 0, 0, 1, 0, 1, and this is by surjectivity, then this comes from a path of projections. So it comes by path of projections, and the and it comes from what I'm trying to do is to get everyone in the room except me to do the work. Okay, I mean, I could have written out a little essay about it. In fact, I probably did at some point in the last week or so, at least roughly. And then I could have projected it onto the screen, or following the old system, copied it out onto the platform. But what I'd like to do is proceed in such a limping way that you rush in to help. Okay? Anyway, think about it. Yeah, of course, you can always peek in the book. There's a key observation, or technical observation, that is that if you look at the so we have the two E and F are the two different projections, and the two those paths are accessible, and we're assuming those are homotopy. But then, so we have a homotopy of these. We have a homotopy of those paths. But then we do apply the proof the surjectivity says that this is actually homotopy to in a matrix algebra, one of the standard paths. Be a path connecting to a path connecting two productions. But the point is that at the end, at the very beginning, what you have at the end is the two given paths. Okay, so you know the two given paths of the two given closed paths starting from the two projections E and F. And if you operate in the whole business by row operation, column operation, row operation. Did what we did with first row operation. The point is that if you do it to the if you do that to something which is linear to begin with, so if you do it, then it in general reduces the degree, and then you end up with the standard path. But suppose that your path, suppose you proof of surjectivity. Suppose you're given a path which is a linear already, and you apply the procedure to it. Well, that's kind of stupid, because if it's linear, then you apply the procedure to it, then nothing happens. But suppose it's the two ends of a whole path of paths, so closed paths, whole path of closed paths. Then the two at the two endpoints in the middle, there are very high polynomial paths, closed paths. And the two endpoints, you have these two linear paths that you started with. Okay? The assumption is they're homotopy. You want to prove injectivity. But then these two endpoints of this path of closed paths the degree is not going to get any larger for them. The endpoints are degree 1 when you start, and they're going to be degree n when you're finished. And by the way, where did this adding multiples of the identity to E and F come from? Well, remember when we changed the trigonometric polynomial, the wrong polynomial, the regular polynomial, and multiply it by the power of z. Well, that's the same as taking E and F and adding multiples of the identity to it. So every time you have a unit, if you start with the unit of the algebra, then the closed path is supposed to be what's the closed path associated to the unit? It's just said, right? Yeah. Okay, so multiplying the path, multiplying that path by z corresponds to taking the e and adding multiples, adding copies of the unit to it. So that's why you get, and that may be necessary because the semigroup, the Murray-Van semigroup may not map injectively into the developing group. That's called having cancellation. It's called being cancelled. That makes sense, right? Because you can cancel. But okay, well, what else? What were some other loose ends? Well, I still said that we can meet again tomorrow, same time, same place. I have a little printout that says we have the room. In case someone else gets it. By the way, was there going to be a tutorial this Friday? Maybe not. Maybe that's it. Maybe not. Oh, good. Oh, good. Good. Yes, tomorrow at 4:45. Oh, good. Okay, well, something I, well, I did say we would discuss the spectral theorem. Well, we could still do that some more. We started talking about it. Remember, there's this nice paper from about 60 years ago now. 1904. I think that's American Mathematical Monthly by explaining how to prove the spectral theorem without using the fundamental theorem of algebra. Also, it's a proof that applies equally well not only to the case of a real Hilbert space, but to the case of a Bernoulli Hilbert space. Sometimes it's used. Yes, quaternions, well, they're useful in mathematics. They're useful in physics too. There's a proof using quaternions. I think that something about when an integer can be expressed as a sum of four squares. Look it up. Sum of four squares. That depends on the fact that it's quite easy to prove that sort of appropriate statement using the fact that like complex numbers, the absolute value squares is the sum of the squares. Real coefficients. With quaternions, you have four coefficients. So we have the square root of some of the square real coefficients. 1 I, J, K. Well, and for that one, for that proof, you don't need to know the real case. You include a proof in the real case. Okay? And the proof already in the real case, it's not quite trivial. You say you want to avoid the fundamental theorem of algebra. But no reason not to use it, maybe, but it's not an elementary, not quite an elementary theorem. It's like the spectral theorem in principle, not elementary. That's a good exercise to before you look up. I mean, I think there is a relatively standard proof. Doesn't just put in terms of in terms of what's called the numerical range. You look at the operator times the vector, and then take inner product with the vector. Okay, and then you look at the absolute value of that. You look at the you divide by the square of the norm of the vector. Take the supreme one. That's called the numerical radius. That's that's of course, we're talking about something going off in that real, based on positive. And if you look at the, but it has a supremum, might or may not be positive. It has infimum, which may or may not be positive. Now, what I recall is if you look at the upper end point, and this lower end point, and one of those must be an eigenvalue. Maybe both. Maybe both. But it's it's easier to work with one. You might as well assume that the operator positive, you added scalar multiple to the unit. So anyway, there's a you just work with inner products, you can prove there's an eigenvalue finite dimension. What does it use about finite dimensions? I would say what it uses the fact that the unit ball in the Hilbert space is compact. And if you look at this number I mentioned, you take the operator acting on a vector, and take the inner product with the same vector, and that's a continuous function. But it's true in infinite dimensions. The unit ball is compact in what's called weak Hilbert space topology. But this function is not. I don't think it's continuous. My recollection is not continuous in the weak Hilbert space topology. It's continuous in the norm topology. The unit ball is not compact in the norm. This has to be this is the way things have to be, because we have examples. Everyone has an example handy of a self-adjoint operator doesn't have any eigenvalues, bounded self-adjoint operator. The function I'm talking about here, continuous on the unit ball, the maximum, the absolute value, well, say it's positive value. Well, maximum or the minimum would be attained by an eigenvector. This is a consequence of Cauchy-Schwarz. Sometime I'm hoping that sometime someone will remind me of the third fundamental fact used in mathematics every day. Supposedly. But one of them is Cauchy-Schwarz, and one of them is integration by parts. Okay. Okay. And why am I jumping up and down on the finite dimensional cases? The Professor Halpern's, the late Professor Halpern's group. Includes the finite dimensional case. You want to look at that and see there's a proof of the spectral theorem for finite dimensions, real, complex, and turning on. It doesn't use when it doesn't use, well, good question, does it use Cauchy-Schwarz? Does any of the funny business that applies to the proof I just referred to, the largest supreme? I don't think it would, because that proof it doesn't work in infinite dimensions, right? Proof that you get an eigenvalue. The operator is A, X is the vector AX in the product of X. You take the largest absolute value of that. That exists in the finite dimensional case. It doesn't exist in infinite dimensional case. So if you have a proof in the infinite dimensional case, it can't be the same as the proof which uses that supremum in the finite dimensional case, right? But one reason I'm talking about that right now is so that we don't have to I guess it's a little tricky. Yep. So you want to know the polynomial is small on the integral from minus the norm of the operator to the norm of the operator. polynomial is small, then the operator you get by plugging in the operator into the polynomial is also small. Then you're finished. The trick involves instead of saying small, just say less than or equal to epsilon, or equivalently greater than or equal to 0 in terms of positivity. And you know if you're greater than or equal to 0, the operator if the polynomial is greater than or equal to 0 on the interval, then the polynomial in the operator is also positive when you plug it in. That would, as a corollary, that would say if the polynomial is small, then the operator is small. Plug in the given operator. And what does this use about operators? Positive operator. I guess it uses that. I guess it uses that if you have an epsilon. Give a little sign that on this point. Give them little pipes to smoke, and then it'll remind people of the picture, the cat with the title painting with the title "Ceci n'est pas un pipe." This is one of the pipes. This is not an official occasion, so I don't have to expect people to speak French. Well, I suppose it is. Okay, so what was I? What did I want to write them for? Sorry? Oh, yeah, thank you. Why did I erase it? That's because nobody could see it. You could see it. That's or maybe you just read my mind. All right. Suppose that we have minus epsilon less than or equal to your self-adjoint operator. And since this epsilon is self-adjoint, you say A is greater than or equal to that epsilon implies that A is self-adjoint. Why is that? Because it means that you take the inner product of A x with x, and saying that, and that's we're saying that that's greater than or equal to epsilon. Okay, and also less than or equal to epsilon. Well, if A is a self-adjoint operator, then for real, yes.
For the left-hand side, is it also positive, or is it minus? For the left-hand side.
Oh, thank you. Pretty restricted. I put it inside or outside. I've got another in the middle. Okay. Okay. Okay, but so this in particular, it's irrelevant because we're assuming A is self-adjoint. But if it is real, if this is real, then and it's a complex. Not in a real for a real Hilbert space, it's always real, right? For any operator. But for a complex, we're supposed to be dealing with. This is irrelevant because we're supposed to be dealing with the full scale or the one steady scale. But if this, in a complex Hilbert space, this is always real. And A has to be self-adjoint. So it's a good exercise. The point is that if A is self-adjoint and this holds, then it's equivalent to saying that the norm of A is epsilon. Okay? This is true in infinite dimensions too, so it's got nothing to do with continuity of the function. Yeah, so and so that's why you can show that if the polynomial is positive, that's why you can show if the polynomial is small, then you plug in the operator, you still get something that's small, because you do get that it's be greater than minus epsilon. Instead of 0, you can put epsilon, right? For polynomial operator would be greater than minus epsilon, less than epsilon. And, so in this sense. Okay, but then that's what we use about self-adjoint operator. Okay. And that's all that comes into the proof of the spectral theorem. If you just, the spectral theorem says you can plug an operator in, plug a self-adjoint operator into a continuous function. And in a way it depends, multiplicative depends, it's a homomorphism continuous function to the operator, the new operator, plug the operator by plugging in the I am speaking, plugging the given one into the continuous function. So that should be a homomorphism. And also it should agree with polynomials. Should agree with like the obvious plugging in when you have a polynomial. And then it should, if the continuous function varies continuously in the suit norm, then the well, plugging in the what follows from this approach. Well, that's what the spectral theorem says. That's one statement of the spectral theorem, and this approach yields that directly. Without, as a consequence of that, you can get to one. If the given operator is unitarily equivalent to a multiplication operator on a measure space, on L2 of a measure space. If you have L2 of a measure space, you have a bounded measurable function, real value function, multiplied by that, multiply L2 functions pointwise on the measure space by that. And that's a bounded operator. L2 over space 1. And that's one form of the spectrum theorem. It's an easy consequence. There's an exercise. You need another exercise. Easy consequence of knowing you have minus or you know that, then it's pretty easy to find the Hilbert space. It's a bit of a trick. It's technically very easy. Okay, you don't need fundamental theorem of boundary both things, but you have to be awake. Okay, that's a good exercise. Not for late at night. If something that's supposed to be easy like this, and you find it's slowing down, maybe fall asleep, you pinch yourself. Oh, that's what I mean. Is try to get your feet on the ground. It's very down to earth. And by the way, it's if anyone is, this is also what you do if you use the Gelfand-Naimark the C-star algebra generated by for the commutative C-star algebra. Easter algebra generated by itself with joint operator. Isomorphic to continuous function. That's a statement very close to this. It leads to the Hilbert space. It leads to the L2 space combination. But that is what I was going to, one reason I mentioned Bielefeld and Riemann. If you look at the theorem for general C geometry, not commutative, they sit on the Hilbert space. The proof of that involves the producing a Hilbert space, right? That's what we want to do here. I mean, we're given Hilbert space is not an L2 space after all. We want to construct an L2 space. So basically, we go ahead and Lamrecht do is construct a Hilbert space. It's well, it's if you look at the construction, it looks a lot like a Hilbert space. Okay. If it were a commutative secret algebra, you apply the Bielefeld-Lamrecht theorem for non-commutative secret algebra 2. Then exactly give you an L2. The Hilbert space would be an L2 space. Okay, well, there's a few minutes, but I maybe then look at some more tomorrow. If we don't finish it today, that could be this business of lifting projections that I mentioned. Okay? Well, you can't do it in general. How many people have done an exercise in the textbook? So it says you can't always lift projections. Okay. That's single figures, single digit. Well, projections is simpler.
Yeah.
Well, suppose you take the C2 algebra continuous functions on a closed interval, which is sort of what we're talking about here. That is what we're talking about. And what's the quotient of that, which has some, any quotient will have a single, at least one projection, at least one non-zero projection, namely the class of the unit, if it's a non-zero quotient. And not the class, the image will equate, the quotient is always classes, and mathematics, almost anything is classes. Right? That's what case theory is. Case stands for class. If you know how to spell it. It will, so what's an example? Well, so is there a quotient? A quotient of this system that has two non-zero projections. Two orthogonal non-zero projections. So any quotient will have a zero projection, and if it's non-zero, it'll have the non-zero one non-zero. Can you express? You can express that unit as a sum of two other projections. Sorry?
Would it depend on?
Well, I'm asking you to search out the suitable quotient. You don't want zero, you don't want to divide by everything. And you don't want to divide by zero. What's something in between you could divide out by? What's an example of an ideal? How do you get an ideal? In terms of looking at the interval, how do you get an ideal? Sorry? Well, okay, but by the way, you you take a single point, then then you get then that will be what's called a maximal proper. Just look at the functions that are zero at that point. And what happens if you take the quotient by that? I guess it's not going to have, maybe it's not going to have very many vectors. Okay. Suppose you, instead of dividing up by a single, instead of throwing away a single point, I guess what's left would be the direct sum of two things, which are point 1/2. And then we direct sum of continuous functions on the upper half converting to 0 and up 1/2, and then the corresponding thing flip it back to the lower half. The direct sum of those two. Neither of them is unity. It's funny, direct sum of the two algebras. Well, that's the ideal. Was that a correct calculation? Well, did I even say what I was calculating? Anyway, if it looks like clowning around, that's a good way of playing. Okay, with calculation, you ask yourself, pick up exercises before. This algebra obviously just has single non-zero projection. What happens if I look at quotients? But by the way, if there were a quotient that had two different non-zero projections, then they couldn't both live, correct? If they were non-equal downstairs, they wouldn't be equal upstairs. You can only have one. You can't have two non-equal non-zero projections upstairs. That would be an example of projections don't live. And for sure, there are lots of quotients that have two. Quotient would be a direct sum of two things. You know what? There's not much time left. Well, we have another month. I just found out today that I was speaking to the microphone. I just found out today that marks aren't due until the 11th of January. Now, we were asked not to wait until then because someone has to look at the marks. But if we say the 10th, I suppose not everyone waits until the 10th. Some people would hand in the things on the 9th. Okay. But, should we just wait and see how it goes, or should I pick a date? Of course, it's not just an anonymous administrator has to look. Someone has to produce marks. That takes time, I guess. Anyway, so there's lots of time to still to play with the ideas in the course in the meantime. And doing homework, it doesn't have to be suggested homework. It can be well, it could be what I just suggested right now. That probably is an exercise in the text. Well, there are all kinds of a good exercise to do is well, I guess that most people have missed taking 436. It's a very good exercise in Peterson on index on the index theorem for tuplets operator. That's very good idea to do that exercise. Okay, I think we're